Today I'm going to share with you some ideas and thoughts on how we can set up an early monitoring for machine learning models, because many of the previous speakers mentioned that building machine learning model is a tough task by itself, but when you deploy the model in production, you start facing a lot of more problems. So now everybody allowed to make any jokes about engineers who cannot actually make some slides. But I'm still a CTO. And evidently so, we are building a tool to analyze, evaluate, and monitor machine learning models in production. So today I'm going to share some thoughts on how we can set up the monitoring at the very beginning. You know that since we deploy machine learning models in production, they start to interact with the real world, with the changing environment, and they tend to work worse and worse with time. And I'm going to share some thoughts on how we can tackle it, especially when we have models with the delayed ground truth. So we will focus on data quality, data drift, and production drift. And finally, I will mention some things of how we can adapt data drift estimation to larger data sets, which is fun because when we build model, we more suffer from a smaller data set, right, and want to get more data. But when we start to apply statistical tests to our data, then it's vice versa. We need to have smaller samples. And finally, I will touch a point on how we can react and what should we do when we face data drift, which is not always a bad thing. So as I mentioned, when we build machine learning model and deploy it into production, sometimes the quality metrics looks somehow like that, and we're trying to catch this moment when model's quality starts to degrade and interact. So the standard solution for this is machine learning monitoring, and I believe everybody agree when we have production service, we need to monitor the service health, data quality, and things like that. So just want to mention that the direct approach for machine learning monitoring is measure something related to quality. Many standard metrics are available here, and it's much better when you understand how machine learning model impact the business. Then you can add some business or product metrics like amount of clicks, views, average bill, and things like that. But there are a lot of cases where it's not that straightforward and you cannot always directly measure their performance. For example, when you have delayed feedback or ground truth, it's pretty often happens when we have some demand forecasting services and we need to predict the demand for some products or services like weeks or months ahead. And in this case, we need to wait until we get this data to directly measure performance, which is not always good. Second case is the problems where we have very volatile target function. And this target function changing by itself, and it's hard to catch this moment when the quality starts to degrade. We always can mix up this with some changes of the target function. Often we apply machine learning models to the objects which can be clustered in many segments. For example, audience segments or different product segments. And in this case, a model can have different quality on different segments. Generally, it's not a problem. We can monitor each segment separately. But for example, when we have a regression problem and we have a lot of segments like 10 or more, and we try to aggregate quality metrics, the aggregated metric can look better than it is. For example, if model tends to underestimate the target on some segments, then overestimate the target function on another segments, then you aggregate the metric and you see that everything is okay, but it's not actually. So there are a lot of cases where we cannot just rely on the performance and we need to add something more. What can we do here? I believe we can take data that we have in hands, even before we get these target function values, ground truth, and start to calculate something. And there are basically three main things that can help here. The data quality, data drift, and prediction drift. So let's discuss them one by one. The data quality is something that we should calculate, I believe, anyway, neither we have batch production model or continuous production model. It makes sense to constantly measure the quality of data because, well, at least from my personal experience, if something goes wrong with the model, that's because the input data is wrong and a lot of things can be catched by solid data quality monitoring. And sometimes people face some problem when they do not have any reference data set and they cannot create the good constants and thresholds based on the reference data. For data quality, it's not a problem, I think, and even if you do not have the reference data, you can start monitor something. For example, you can measure general things like amount of missing data, amount of constant features or almost constant features, correlations, because probably sometimes you do not want to have in our dataset features that correlate with the model's output highly, or maybe pair correlations and things like this. You can come up with some range for different features based on the domain area knowledge. So there are a lot of things that we can measure even if we have no reference data. When we have some reference, it became easier because, well, now we have some base to compare with, and you can take the data from the training phase or from the previous batch of model usage, and based on this data, create some expectations. For example, some expectations about descriptive statistics that you can calculate on top of features. And here there are two basic approaches that one can use. The first is calculate some descriptive statistics like means, quantiles, medians on top of the reference data set. Then calculate the same on top of the current data and just compare them by seeing difference. This is a pretty straightforward and simple approach which can help to get some basic problems with the features. But of course everybody knows that when we perform some point-wise estimation of such statistics, if you have any outliers or stuff like this, then it basically break all the estimations and we can get a lot of false alerts. To make it a bit more robust, we can use the interval estimations for all the statistics and use some statistical tests, for example, to compare means, medians, and get some confidence interval. So if you need a more robust approach, I would suggest to go for the second option. So this is something we can measure based on our reference data. Compare what we have with what we had before. Second thing is a bit more interesting, I believe. It's a data drift. This is the change of distributions on top of the distributions of input features or output of the model. Sometimes when there are some changes in such distributions, it's not a problem because, for example, we can have some trends, for example, linear trends. We can have some seasonality and, of course, if we have it, the distribution will be different. But if there is some shift in distributions for key drivers of your model and you do not have, you cannot get any reasons why the distributions should be another, then this can be the early signal of a potential problem. So this is why measuring data drift is quite important on early stages where you still do not have a ground truth. And there are pretty interesting calculations because there are a lot of degrees of freedom. So which statistical test to choose, where is the threshold, and many questions like this. So let us discuss them one by one. So first of all, I want to mention again that when we talk about data drift, it's not only about features. You can apply the same logic to prediction, and it works pretty well when you have the history of previous models application. In this case, you just compare the distributions between them. But if you use the training data as a reference, don't forget about training service queue and lower down a bit some expectations on the prediction. So the question is how we detect data drift, how we define it. And the most popular approach nowadays is using statistical tests. I would rather say that you can use any evaluation process that you can come up with to compare two distributions, but in most cases, this is actually statistical tests. And there are two basic approaches to do that. First, using some parametric testing, and second is obviously using some non-parametric tests. And I believe both approaches make sense. So there are some considerations I want to share on how you can select the approach for the specific case and specific features. And the first is parametric tests. Often when we build machine learning model, we can say that we have some golden features, the key performance, and some like secondary important features. And when we talk about these main features, in most cases we can interpret them, we can generate some expectations on how these important features should be distributed, and maybe even generate some hypotheses about the parameters of such distributions, like means, standard deviations, and things like this. And in this case, I would suggest to use parametric tests to check whether your important features are distributed exactly as you expected. Z-test, t-test for mean, for example, or one proportional z-test if you have a binary feature works well here. The good thing is that you don't really need the reference to do this if you compare, for example, the mean of your distribution with some constant. But if you have reference, it also works well. And of course, to samples to compare parameters between the reference and current data. So this is something that works pretty well. The advantages are that generally, always, yes, parametric tests are more sensitive than non-parametric, so you can detect drift earlier. But the disadvantage is that you still need to come up with some expectations on some parameters of your statistics, especially if you use one sample tests. And the second is that such tests are more demanding. For example, some of them you can use only if you have normally distributed data and things like this. So it's not a very general approach, but for some key important features, it works pretty well. On the second hand, we have non-parametric tests, right? So these are tests that does not have they have much less demands about the feature distributions, right? And you can calculate it more or less on any features. So here are a lot of different tests that can help. Here, in most cases, they just compare distributions between each other or answer the question whether two samples were generated by the same distribution. And they work pretty well. So here I can suggest something like Kolmogorov-Smirnov or K-sample test for numerical features. It works pretty well, I would say. Nowadays, a lot of people prefer calculate distances between distributions instead of tests, which is also a nice approach. I personally like Westerstein distance, which is also known as Earth mover's distance. Works pretty well, but instead of p-value, you get this distance, right? So if you used to set up your monitoring based on p-values, it will be a bit more complicated, I would say, but still can work. And for smaller data sets, you can use something like exact tests, Bernard or Fisher's, which is also helps to detect drift on smaller data sets. So there are a lot of different statistical tests that can be applied there. One disadvantage is that the non-parametric tests are less sensitive, so you will detect drift later on, but you can automate this process because you can apply and select the exact statistical test just based on type of the feature and sample size, I would say. So evidently we built dashboards to detect, which helps to detect prediction drift and drift of features, and you can automatically select the exact test that should suit for each feature. So this is open source again, and if someone is interested, you can just go to GitHub and try it. And there are a lot of tools like this that helps you to select tests automatically. So I think it can be done in Selenium Alibi, in Emeli, in deep checks. So if you're interested, there are a lot of tools that can help with that task. Yeah, works perfect. So I wanted to mention two more things. One related to non-batch models and another related to bigger data set. But let's just discuss it right there. So often when people start trying to use statistical tests to detect drift on larger data sets, they face with the problem that they almost always have a drift, right? So you start to apply your Kolmogorov-Smirnov test and you see that the samples are different. And this happens because the sample sizes are huge. If you will try to apply statistical test for data sets like with hundreds or thousands of objects, there are higher chances that there will be some differences and you will see some small p-value and detect drift. So I suggest to remember that statistics was made to work with samples, right? And it makes sense to sample your data first and then calculate drift on top of it. So there is two general approach how you can create these samples. First is just by sampling the data, right? Random sample or maybe stratified sample. If you have unbalanced classification problem, then you can account for it. And then apply statistical test to these samples. And second approach is actually bucketing. So you can split your data into several buckets, let's say 100 or even less, and average the feature value there, and then calculate statistic on top of this averaged buckets value. It's from one point of view, it's easier because you do not need to come up with the sampling strategy, so you just take all your data, but you still solve the problem with the data size. So it also can help to make more reasonable results. And there are more approaches, more theoretical one, I would say, but practically I would suggest either go with sampling or with the bucketing. The second big problem with drift detection is non-batch models, because to apply statistical tests, we basically need two samples, right? So the reference and current data, let's call them like this. But when you have a continuous data stream, how to generate the second data set, right? Because you have like stream of the data. And here I would suggest to use some window function. For example, create the static reference from training data or manually selected, and then use some window function to continuously generate some current data sets and calculate statistical test on top of each window. The strategy can be very different because we need to decide on the window size, we need to decide on how fast we move this window, right? And some even use the moving reference, because sometimes it makes sense even move your reference data sample in order to calculate drift better. So there are a lot of, like, it's very debatable. I mean, the strategy on how you should, how exactly you should generate these windows, but it works pretty well. And if you have streaming data, you still can calculate statistical tests on top of it. It will work fine. Yeah. So second question I wanted to tackle, but I really want to get the slide, is how you select the statistical tests, because it's sometimes an issue. Yeah, and there is two nice approaches I want to suggest here. So first is just go for defaults, because I just mentioned there are quite a lot of tools nowadays that help you to do it, and a lot of them are open source. For example, like ours one. So you can just start monitor your data using some default strategy, like Kolmogorov-Smirnov for numerical features, using bucketing, Pearson chi-square for categorical data, and z-test for binary data, right? Something really simple, and start monitoring like this. Later, you will see whether you get too much false alert or maybe you're missing something, and based on this feedback, you can adjust some thresholds or maybe choose another statistical test. So this is like a fast start to monitoring. And second option is a bit more complicated, but if you have some historical data about your previous models run, you can use it to adjust your monitoring schema. I would suggest the algorithm where you take the stable period of time where you had no drift and apply all the test candidates you have. Then you compare p-values and you take the test where you have the lowest p-value, so the most sensitive test, but one that still does not detect the drift. So this is how you can choose the most sensitive but not overreacting statistical tests. And if you have some period of time where you had drift, or maybe you can generate it yourself by just synthetically changing some data, you can check that the test you selected actually can react on this. So that's how you can decide on the monitoring design using historical data. The last thing I want to mention today is how actually you react on data drift, because, well, it's always depend on the context, right? It's not always a problem when you see data drift, but it might be. And there are a lot of different things you can do, starting from changing the business logic of model application. For example, if previously you automated your pipeline by using machine learning model, and if you detected some drift, you can now send some objects for manual review, for example, just because now we are not that sure that model works correctly. And we can retrain model, rebuild it entirely, and do many, many different things. The question is how to decide whether the data drift is a problem or not, and here I just want to say that it depends on context highly, and I want to drop a couple of examples of how it can be. Let's assume that we have data drift detected, but our prediction drift is not detected. So model's output hasn't changed, but some distributions or some features has changed. It can be a positive scenario. For example, only non-important features are drifted. And the model is robust enough to survive it. In this case, we can just continue using the model and no intervention is needed. But it can be another scenario where all important features has drifted, but model output stayed the same. This is actually a problem because when you clearly see that something has changed, the environment has changed, but model didn't react. Right? Probably model just cannot extrapolate well, right? There are some machine learning models that cannot, for example, make any prediction outside of the range of values it was trained on. And in this case, probably we need to do something. So this is the negative interpretation on data drift. And another scenario, for example, data drift is detected on top of the features, and data drift is detected on top of model predictions. So predictions and features has changed. So here can be positive scenario, actually. For example, if you see that some important features changed, for example, some prices get lower, and model started to predict higher sales. That's logical enough, right? So probably model can extrapolate well, and we can continue to use this model. But if, for example, important features changed and model changed its behavior, but in very non-intuitive way, then probably you shouldn't continue to use it and should to at least make sure that it makes sense, or maybe retrain your model on top of new batch of data. So this is the difference of the interpretation of data drift and prediction drift. Of course, even if we use some existing monitoring designs and monitoring tools, we need to come up with this logic on how to react ourselves. But anyway, as a conclusion, I want to say that early monitoring makes sense for a lot of cases, and it really makes sense to at least start monitoring your model as soon as possible using some defaults, and then adjust them to suit your use case and your models. So this is all I wanted to share with you today, and happy to discuss some details.
Thank you very much, Emeli. I think we have time for maybe one or two questions, and then I have a couple of quick announcements. Yes.
Thank you, Emeli. I have a quick question. So if you have, for example, 2 years of data, maybe instead of just kicking it off and monitoring and trying to catch data drift, do you think it's a good idea maybe to have this hold out data and try to catch data drift in past to know what to expect in future?
That's a very nice approach. I'm actually a big fan of using historical data to generate some expectations at least, and I think this is the very good idea, especially in cases where you have strong seasonality. Because if you just continue doing what I suggested with the moving windows and you have strong seasonality, then definitely you will detect drift each time. But if you use the whole period of time, for example, the whole year from previous data, it will be much easier to get more reasonable results. So I think, yes, it makes sense, especially when you have this historical data and, for example, when you have seasonality. If you do not have historical data, then probably you just don't have this option.
Thank you. I think we have time for maybe, yes, one more question.
Thank you so much for the talk. So the question is more regarding the methods that you presented. So I assume that most of them work if you have your model which works with the uniformly distributed data. What if your model predicts some rare events, and most of the time you have no, and once in a while you get yes? How you can detect the drift in this situation?
Very good question. When we have something like this, I would go for a bit another approach. For example, this really depends on how often do you have these spikes. And if it's some binary target function, there are some statistical tests which can compare the share of, just compare shares. for example, the z-test proportional or t-test proportional test. So we can apply this to compare shares. For example, if you previously had like 10% or 1% of this target events, and now you have like 3% of these target events, you can just compare these values using statistical tests. So proportional would go for it. And one more thing here, sometimes it makes sense to use outlier detection instead of data drift. And if we are talking about really rare events, then probably if you implement the outlier detection procedure and will compare the amount of outliers that you detected with the previous windows, then it would make sense for such data.
Thank you, Emeli.